So how do you build a system that connects millions of people in real time, all from a blank whiteboard? Well, today we're going to tackle that exact question by breaking down one of the most classic system design challenges out there, designing Uber. Let's jump right in.
And this right here, this is the heart of the problem. It's not just about building some app, it's about orchestrating a massive, real-time marketplace, handling just incredible amounts of data, and making sure the experience is seamless for millions of people at the exact same time. So for this, let's pretend we're in a real interview and solve this thing together step by step.
Okay, so here's our game plan. First, we're going to really define the problem, nail down what we're building. Then, we'll lay down the foundation with our basic data model and APIs. After that, the fun part, building out the core features. Then we'll stress test our design and see if it can handle Uber-level scale. And finally, we'll talk about what really separates a good answer from a truly great one in an interview.
All right, first things first, and this is probably the most critical step in any system design interview. You have to stop, think, and define the problem. Before you draw a single box on that whiteboard, you need to agree on a blueprint. What are we actually building? And, maybe even more importantly, what are we deciding to leave out?
So first up are the functional requirements. This is basically our what does the system absolutely have to do list. Now, to keep ourselves sane and focused, we're going to prioritize this core loop you see here. You get a fare, you request the ride, you get matched, and the driver accepts. And notice, we are explicitly calling things like ratings or Uber XL out of scope. This is such a key move in an interview because it shows you can manage complexity and prioritize what really matters.
And now for the non-functionals, or the how well does it have to do it list. These are the qualities that make the system feel amazing instead of clunky. We need low latency, right? Nobody wants to wait 5 minutes for a match. We absolutely need strong consistency to prevent total chaos. And we need high throughput to handle those crazy surges in demand. Like when a big concert lets out and everyone wants a ride at once.
Okay, let's pause for a second on that term, strong consistency. What does that really mean? Well, think of it as a guarantee. It's a promise that when we update a piece of data, like changing a driver's status from available to booked, the entire system sees that change instantly. This is what stops the same driver from being offered to two different riders at the exact same moment. It's what keeps the whole marketplace orderly and fair.
Okay, with our blueprint set, it's time to actually start laying the foundation. We're going to start by defining the core nouns of our system, the data entities, and then we'll design the doors that our apps will use to talk to the system, our APIs.
So these are the fundamental building blocks, the main pieces of data we'll be juggling. You can see everything really centers around that ride object. A rider and a driver are obviously connected to it. The whole process kicks off with a fare quote, and of course, during the whole trip, we're constantly tracking the driver's location. Simple enough, right?
And these APIs are basically the contracts for how our mobile apps will talk to our backend. We use post when we want to create something brand new, like a fare estimate or a ride request. Drivers will also be constantly sending a post with their new location. Now we use patch when we want to modify something that already exists, like when a driver accepts a ride, changing its status from pending to accepted. All right, our foundation is officially in place. Now we can get to the good stuff, actually building the high-level architecture. And the best way to do this without getting totally lost is to just tackle our functional requirements one by one, building up our system piece by logical piece. Okay, let's trace that very first action, getting a price. So the request starts on the rider's phone. It goes through our API gateway, which then smartly routes it to a dedicated ride service. Now this service is clever. Instead of trying to calculate routes itself, which is super hard, it just asks a third party, like Google Maps. It gets the distance back, crunches the numbers for a price, saves it all to our database, and sends that fare right back to the rider.
Now let's talk about that API gateway for a sec. Think of it like the single front door to our entire complex system. It's the traffic controller, making sure requests end up at the right internal service, the ride service, the location service, you name it. But it's also a security guard, handling things like authentication so that each little service inside doesn't have to worry about it.
So getting a fare is one thing, but finding a driver, that's where the real magic happens. To pull this off, we need to extend our design. We're going to introduce two new specialized services, a location service, whose only job is to keep track of where every single driver is, and a ride matching service, which holds all the complex logic for finding the best driver for a particular ride.
Okay, so our ride matching service finds the perfect driver, but how do we let them know? We can't just hope they have their app open.
We need another piece, a notification service, to send a push notification that goes directly to their phone. They see it, tap accept, and that tells our ride service to update the status. And just like that, the core loop is complete.
Now, what about seeing that little car moving on your map in real time? Just asking for updates over and over again is really inefficient. That's where technology like WebSockets comes in. See, unlike a normal request where your phone has to keep asking, "Where is he now? Where is he now?" a WebSocket opens up a persistent two-way street. This lets our server push those location updates directly to the rider's phone instantly, which gives you that super smooth, live tracking experience.
Okay, so we've got a working system on the whiteboard. It does everything we said it needed to do. But in a senior or a staff-level interview, this is where the real conversation starts. Having a design that just works isn't enough. Now we have to prove it can handle the absolutely enormous global scale of a service like Uber. So this brings us to our first huge, and I mean huge, scaling problem. We have millions of drivers on the road, all of them sending us their location every few seconds. How do we possibly ingest all that data without our servers just melting? And then, once we have it, how do we search through it fast enough to find nearby drivers in milliseconds? In this number, this just perfectly illustrates the insane scale we're talking about. I mean, if Uber has, say, 10 million active drivers, and each one sends a location update every 5 seconds, that's 2 million write operations every single second. A standard database, like the kind you normally use, just can't handle that. It would fall over. We need a totally different tool for this job.
And the other half of that problem is finding drivers quickly. You see, a standard database index, a B tree, it's like the index in the back of a book. It's great for finding a specific page number, but it's terrible for finding all mentions of a topic within a range of pages. That's why we need a spatial index. It's a special tool designed from the ground up to answer geographic questions like, find me all drivers within a 5-mile radius, and to do it almost instantly.
Okay, next up we have to tackle that concurrency problem we talked about way back at the beginning, our strong consistency requirement. With millions of requests flying around, it's a mathematical certainty that two different processes will try to grab the same available driver at the exact same time. So how do we enforce a lock on that driver? This is where you start talking about things like distributed locks, maybe using a super fast in-memory database like Redis.
And what about reliability? Think about it. In our current design, services are talking directly to each other. So if the ride matching service gets a request, but then crashes a millisecond later, that rider's request is just gone. It vanished into the ether. That's a horrible experience. So we need a buffer, something like a message queue, think Apache Kafka, that can reliably hold on to these requests. That way, even if a server fails, the request is safe and sound, ready to be picked up.
So we've designed a functional system, and we've poked holes in it to find the major scaling challenges. This last part is all about how you actually communicate this stuff in an interview, because the depth of your answers and your ability to proactively find these hard problems is exactly what separates a mid-level candidate from a senior or staff plus engineer.
And this table really breaks it down nicely. At a mid-level, the focus is on breadth. Can you get a working system on the board? For a senior role, it's all about depth. Can you talk about the trade-offs of your choices? Can you solve for scale? And then at that staff plus level, it's about proactivity. They expect you to be the one to find these deep, tricky issues, to lead the conversation, and maybe even teach the interviewer a thing or two.
And so, I'll leave you with one final question to chew on. We've built this system with all these different services, but what's its biggest single point of failure? If you look at our design, what is the one component that, if it goes down, takes the whole thing down with it? Answering questions like that is the real key to building truly resilient systems. Thanks so much for tuning in.